Okay, in 6.3, we studied vector addition and multiplication by a scalar amount, which means we just had a number out front, like maybe we had 2. For instance, we might have had 2 times the vector 1, 3, and this would be a this would be called a scalar because it's just a number. A number, when you have a number, a lot of times they call it a scalar quantity. This would be a vector quantity because it's a vector. It's written in this form. It doesn't have the i's and j's, but that's okay. So I could multiply that, and I get a vector out of it because I just say, well, 2 times 1 is 2. You're just distributing, aren't you? 2 times 3 is 6. I get a vector out of that. Sometimes, though, we have certain types of operations where we get something called a dot product. And the dot product that we get is a scalar quantity. It is scalar. It's going to be just a number, basically. So we're not going to get a two-part kind of thing. We're just going to get a number out of it. And a dot product is an operation, which means we need 2 vectors to do it. So let's say I have a vector u, and I'm going to say that it's u1, u2, okay? That's a 1, it looks like a comma, but u2. And I got a vector v, and that maybe I represent it as the first part's v1 and the second part's v2, okay? Well, if I want the dot product, I would write it like this. This is not, it's a dot product of the vectors. Usually they're going to give you that in the find the dot product, so you don't get it confused. And it's a number, and how we find this number is we multiply u1 times v1. We multiply the 2 first parts, and then we add in the second parts of the 2 vectors multiplied together. Let's look at examples. Okay, so if I want to find the dot product of these 2 vectors, that's 1, 2, I could have written it this way. Instead of saying that find the dot product, I could have written it as this. I could put a dot between them. Looks like the multiplication dot. Okay, we didn't really multiply whole vectors times whole vectors, if you remember in the last unit. So this is sort of the multiplication for vectors, I guess you'd say, when you got the 2 whole vectors. So what I'm going to do is say, okay, I'm going to multiply the 2 x kind of parts, okay, so 2 times 1, and I'm going to add in the y parts multiplied together, so that's negative 1 times 2. Well, 2 times 1 is 2, and then negative 1 times 2 is negative 2. 2 plus negative 2 is 0, which is just 0, okay? Actually, it's not a vector. I don't know why I wrote it as a vector. It's a number, and it's 0, okay? Now, that's, if we're going to find out later on, there's something special about if we multiply, if we find the dot product and it's 0, then what? This is a special one. I'm going to go ahead and tell you that it is. We get all kinds of numbers here, okay? But this is a special thing that happens when we actually get this 0 here. When you get a dot product of 0, that means that the vectors are orthogonal. And orthogonal is another word for perpendicular, basically. And I know in our calculus class we have problems that ask us to tell if 2 vectors are orthogonal or find an orthogonal vector. So that basically means these 2 vectors meet at a right angle. Pretty much means the same thing as perpendicular. So one thing, it is special to get 0. This is not going to happen all the time. It's only going to happen when we have perpendicular things. If you remember when we were looking at slopes of perpendicular lines were opposite reciprocals of each other. So this is kind of a special case for vectors. What do we do when we're looking at vectors? It's not the opposite reciprocal anything, is it? It's just that one thing you might notice, though, aren't the numbers switched and the signs are opposite on one of them, not both of them, though. Anyway, that's just something interesting to note. Now, we can talk about this orthogonal vector. I can have 0 dot v which is just like the scalar 0 times some vector with two parts to it, and that's always going to be, well, actually, no, that's not true. It's not a scalar. It's, what if I had the vector 0, 0 dotted with any other vector? It's always going to be 0, 0, isn't it? So it's always going to be 0 plus 0. I don't know why I keep writing these little symbols there, because this is not a vector, it's a scalar quantity. So I'm going to make the mistakes and then reiterate to you that I made a mistake. The result is just a number 0. And what I know about this then is that the 0 vector is orthogonal to every vector. So that's one of the rules that you'll see listed under properties of the dot product. The 0 vector is orthogonal to any vector. Okay? There's some other properties we need to know. U dot V is equal to V dot U. If you remember, that's really kind of like the commutative property. It is the commutative property. Commutative property basically holds for vectors. If I have two vectors and I choose one to go first one time, and then I decide, well, maybe the person next to me, I look over at their paper and they chose the other one and did it first. Well, it's not going to matter. We're going to get the same result. They're commutative. So that's one property we need to know. Also, if I have a vector dotted, a dot product of a vector, and let's say I've got two vectors added together and then I'm going to dot product them. It's equal. I could do the problem that way. I could add the two vectors first and then multiply or dot product the new vector with the vector. Or I could, this is kind of like a distributive property, I could have U dot V and figure it out first. And then I can have U dot W, and I can add those numbers together, and those two sides are going to be equal, basically. So that's kind of like a distributive property if you want to think about it for vectors. All right. If I take a vector and I dot product it by itself, I'm going to get the magnitude of the vector squared. Magnitude of the vector by itself squared. So that holds. And then another property is if I have C is all, when they put UC in these sections, it's always a scalar amount. So like if I had 2 times U dot V, that would be the same thing as CU dot V, or I could do it as U dot C times V. If you notice, I'm not going to have CU dot CV. It's not distributive in the way that we would normally think, is it? It's, distributive only, the property only holds when you have a plus or minus. For instance, up here, this was really the distributive type property, and I'm sure it would hold with subtraction as well. That's a distributive property because there's a plus there. Here, I have a dot product and a scalar out front. So if you think about it, think about numbers and how you do them. If you had 2 times 3 times 4, I wouldn't distribute the 2 times the 3 and the 2 times the 4. Though as a teacher, I see people do it all the time. They get confused. The distributive property only holds when there's a plus or minus, like that one circled up above on the higher part of the tablet. I don't say 2 times 3 plus 2 times 4. There's not a plus there. It's a dot product. So basically, I can take the first vector and multiply it by 2. So I could say 2, I'm sorry, we're talking about numbers here. I could say 2 times 3 and then multiply it by 4. Or I could do 2 times 4 and then multiply it by 3, basically. So you're going to put the scalar quantity with one of the vectors. So multiply one vector times the number out front. So let's look at that for vector. If I had 2 times, let's let U be -1, 3. That's a vector. And let's let V equal 2, -4. Okay, so if I had 2 2 times u dot v, I could either double the u and say, okay, if I double the u, that's 2 times negative 1, 3, and dot product that with 2, negative 4. So I would do the inside the parentheses first. And let's just see what that would be. That's going to be, if I just multiply, that's going to be negative 2, 6 here. Then I need to draw the little triangle. Then if I dot product times 2 times negative 4, if you remember now, how do we do this? We go negative 2 times 2 is negative 4, plus 6 times negative 4 is negative 24, and negative 4 plus negative 24 is negative 28. I multiply the x parts together, I multiply the y parts together, and then I add them. So I got negative 28. But what if I did it with the other one? What if I had negative 1, 3 as a vector, and I had it dotted times 2 times the other vector? Okay. Am I still going to get negative 28? Let's see that it holds true. That's negative 1, 3, dotted. Okay, now 2 times 2, negative 4 would be 2 times 2 is 4, and 2 times negative 4 is negative 8. All right, so let's figure out the dot product over here. Negative 1 times 4 is negative 4. I'm going to add in the y parts multiplied together. 3 times negative 28 is negative 24. Negative 4 plus negative 24 is negative 28. So yes, we do get the same result. So that's all that property is saying. So just wanted to clarify the properties before we go on. We have uses for dot products, and I'm going to show you those, but I wanted to go through the properties first before I got into all those things, because they're going to make you use some of these properties.